Hi everybody, Dr. Tom McNamara back again for our course in trigonometry. In our last video we discussed how the graphs of sine, cosine, and tangent behave. In this video we'll discuss the remaining trig functions, secant, cosecant, and cotangent. Alright, so let's get started with, let me go over here so I can give myself some nice room there. And I'm going to start out by doing a little review here, and I'm going to graph the function y equals cosine x. Okay, so this axis, I'm going to plot my angles in radians. Okay, now the key points to pay attention to when you're dealing with the cosine function are multiples of pi over 2. So pi over 2. Pi is important. 3 pi over 2. And finally 2 pi. Okay, those are all key places. And we remember that the cosine function, the output values live between -1 and +1. Okay, now when you're dealing with the cosine function, your picture starts up here. Cosine of 0 is 1. Cosine of pi is 0. -1, back up, and then to the top. Okay, so when we're plotting the cosine function, we start up here, we hit the midline, we bottom out, back to the middle, and then up top. We connect these with a nice smooth curve. Okay, so no angles when you're graphing your trig functions. No sharp corners, smooth turns. And also, make sure you get this right. You'll understand why the graph looks like this when you take a course in calculus. You can talk about how things bend and how you can tell how things bend. But for right now, just take my word for it. Kind of bending down there, bending up here, bending down. All right, now, I want to go ahead and talk about secant x. Okay, I know here I said theta, here I said x. You'll need to get comfortable switching between the different variables. A lot of times we use theta for our angle, but there's no reason we have to use that variable name. We could just as well use x. Okay, now, we know that secant theta is 1 over cosine theta. Or, with this variable choice, secant x is 1 over cosine x. Now, whenever you got division, you gotta be a little bit concerned about 0, okay? You can't divide by 0. Now, cosine is 0 here and here. So, our function, secant, is going to have vertical asymptotes at those places. Okay, now the question is, what is going to be happening when we get close to those places? And I want to make a few notes here. If I take the reciprocal of a number, let's say I take the reciprocal of 1/2, okay? The reciprocal of 1/2, well, would be 1 over 1/2, 2 over 1, so the reciprocal of 1/2 is 2. Let me take something even smaller. The reciprocal of 1/10, well, the reciprocal of 1/10 would be 10 over 1, or just 10. Okay, so 1/2 compared to 1/10. 1/10 is smaller, and its reciprocal got bigger. If I go even smaller, let's say 1 over 100, take the reciprocal of that, well, the reciprocal of 1 over 100 is 100 over 1, or just plain old 100. So the point I want to emphasize is that if I'm taking reciprocals of numbers, and those numbers get closer to 0, like this is getting here, right? This is 0.5, this is 0.1, this is 0.01. Take the reciprocal of 0.5, you get 2. Take the reciprocal of 0.1, you get 10. Take the reciprocal of 0.01, you get 100. Okay, so when you're taking these reciprocals and your numbers are getting closer to 0, your reciprocals are going to balloon up. They're going to get bigger and bigger and bigger. So as my input goes towards pi over 2, if I'm talking about the secant, well, I'm talking about taking reciprocal of cosine. Well, in this section, we can see the cosine is getting close to 0. So the reciprocal is going to balloon up. The reciprocal is going to be up there. Okay, the secant function is going to look like that. Down in this section, I'm going to get a similar picture, but reciprocal of a negative number is still negative, so we're going to have that. And over here I got this. Okay, so wherever the cosine function is 0, the secant function is going to have an asymptote. If the secant function is positive when it approaches that asymptote, we're going to balloon up. If the secant function is negative, the graph is going to plunge down. Okay, so the secant function is going to look like this picture I've drawn here in the orange. Hopefully that's coming out. Yeah, I think you can distinguish between the two colors. Okay, so secant function has these asymptotes where the cosine function is 0. If you're in the positive area, if your graph is above the x-axis when you approach an asymptote, balloon up. If your graph is below, when you approach an asymptote, you plunge down. Now, because the cosine function is periodic, the secant function will also be periodic. So if you're saying, okay, what does the graph look like over in that region? Well, take this exact picture, take the orange picture, and draw it again right here. If you want to know what it looks like in this section, take this exact picture of the orange graph and draw it right here. Okay, so we're going to get these kind of U-shapes repeated over and over again by the periodic nature of these functions. Okay, we can do a very similar process to get the graph of cosecant. Now, if we're dealing with the cosecant function, cosecant is the reciprocal of sine x. So let me start out by revisiting the graph of the sine function. Once again, we know the sine function lives between 1 and -1. The key places along the horizontal axis for our sine function are going to be pi over 2, pi, 3 pi over 2, and 2 pi. Now when you're graphing the sine function, we start here. We start at the midline, go up to the top, back down to the midline, bottom out over here, and then back to the middle. Connect these with a nice smooth curve. And we've got a graph of the function y equals sine x. Okay, now once again, we're going to deal with the reciprocal of this. So let me draw that in orange, cosecant x, or what we know from the reciprocal identities, 1 over sine x. As we discussed, we're going to have these things called asymptotes. A vertical asymptote is basically a vertical line that the function can't cross. The function's graph cannot cross that vertical line. Now, the cosecant function is going to have vertical asymptotes wherever the sine function is 0. In other words, 0, pi, and 2 pi. And as we discussed before, if you're above the x-axis and you're going towards a vertical asymptote, you balloon up like this. If you are below the x-axis and you go toward an asymptote, you plunge down like that. Okay, so the graph for the cosecant function also has these asymptotes. It's going to be periodic, so you want to know what the graph is going to look like over here? Take this exact picture in the orange and draw it again. We'll have a U shape up here and another U shape down here. What does it look like over here? Well, take this exact picture and copy it right here. We'll have an upside down U shape right here and a right side up U shape over there, okay? They're all periodic. Okay, the sine, cosine, they have period 2 pi, and so do the secant and cosecant. They have period 2 pi. All right, so one more picture for us to work out, and that would be the cotangent function. Ooh, lost my grip on the eraser there. All right, now, I'm going to start out by drawing the picture for the tangent function. Okay, so in the white, I'm going to draw y equals tangent x. This is something we drew last time. Now, when you're drawing graphs for sine, cosine, secant, cosecant, the points I want you to plot on the horizontal axis are 0, pi over 2, pi, 3 pi over 2, and 2 pi. Those are our anchor points for those functions. Now, the reason is because those functions, sine, cosine, secant, and cosecant, those have period 2 pi. But if you look back in that last video that we posted, the tangent function has period pi. So our key points here are going to be these guys. Pi over 4, pi over 2, 3 pi over 4, and pi. Okay, so now the tangent function has asymptotes at pi over 2 and pi, etc. Oh, actually, no, I guess the tangent function is 0 there. Okay, so this is what my tangent function is looking like. So let me think about y equals cotangent x. Okay, zeros of tangent will become asymptotes for cotangent. Okay, zeros for tangent become asymptotes for cotangent because, right, we know from the ratio identities that tangent is equal to sine theta over cosine theta. So tangent, I'm using the variable x right now, so I'll replace these with x's. Tangent is going to have an asymptote whenever cosine is 0. Cotangent is going to have an asymptote whenever sine is 0. Okay. Now I mentioned that the zeros for the tangent function turn into asymptotes for the cotangent function, and vice versa. The asymptotes for the tangent function will be the zeros of the cotangent function. So our picture for cotangent is going to look like this. Okay, here the graph of tangent is above, so when we approach this asymptote, which is the asymptote for cotangent, rocket up. Here the graph for tangent is below. As we approach this asymptote for cotangent, we plunge down. What does this section over here look like? Take an exact copy of this picture and draw it again. And repeat that forever, for however far out you want to go. Same thing on this side. Okay, so you can get the graphs of the remaining trig functions by using the graphs of the 3 functions that we talked about in the last video. Remember, zeros of the original function turn into asymptotes when you take the reciprocal, which is what we're seeing right here. The zeros for the tangent function, which were at 0 and pi, the zeros turn into asymptotes for the cotangent function.